Today we're going to talk about chapter 23, which is the flow of electricity or flow of charge, what we call current. We're going to study electrical current in this chapter. We'll talk a little bit about, a lot actually, about how to make electric current flow, particularly in a wire, conducting wire that is able to carry electron charges through it. We'll talk about the voltage sources that are used to generate that current. Then we'll get in a little bit into how that current is related to the resistance in the wire for which the current is flowing, and et cetera, et cetera. We'll talk about some of these other points as we go through as well. So to begin with, we'll talk a little bit about the analogy with water flowing through a system of reservoirs and pipes. And this will help you to understand the analogy between water flowing through a tube and electrons flowing through a conducting material like copper, aluminum, silver, gold, all of the materials that are conducting. When the ends of an electrical conductor, which is a material which basically has very loosely bound electrons that are free to move throughout the system. When the ends of the conductor, and we can think of this as a long wire, for example, are at different electric potentials, then that is when we have a potential difference and the charge flows from one end to the other. The analogous idea with water is that water will flow from high pressure to low pressure. So in this case, we see that higher elevation of water in the tank on the left will tend to push the water through the bottom of the tank until the two levels of the water equalize. And at that point, we then have the current has dropped to zero because there's no more flow of water once the levels on both sides have equalized. So that's the basic idea. I want to refresh your memory a little bit about electric potential. In the last lecture, we distinguished two concepts of electric potential energy and electric potential. In one case, we leave off the word energy at the end, and in the other case, we don't. We leave it on. The electric potential energy, or I should say the electric potential, refers to what we normally call as voltage, and it is the potential energy per unit charge. We would expect, for example, a highly charged object in an electric field to accelerate more quickly than a smaller amount of charge in an electric field. But if I take that's because of the electric potential energy. But if I take that potential energy and divide it by the charge, then for those two objects, it will be the same. It's a little more abstract, but it's potential energy per unit charge. And that's what turns out to be the driving force in a circuit, which is related to the concept of potential difference. That there's a difference in electric potential or potential energy on one side than the other. Here you have a higher amount of potential energy in the water tank on the left than you do in the water tank on the right. That means that there is a difference in potential energy, which we refer to as mass times G times H in the mechanics section of the class. And that potential, which is also a difference in potential energy, causes the flow of the water through the tank. So that's the idea of this, and that's the analogy with water flow. To attain a sustained flow of charge in a conductor, some arrangement must be provided to maintain a difference in the potential. So the basic idea here is, again, we're going to revert back to the concept of the water tank, only now what I'm going to have is a pump added onto the system so that as the water begins to flow from the higher potential to the lower potential, then in order for it not to come to equalize to the same height, I have to continuously keep pumping water through here to keep this potential higher than this potential over here. And when I do that, then I will be able to maintain a stream of water current because the pump is applying the pressure to keep the water flowing through into the tank. And by analogy, talk about electric potential. The pump, which is obviously a pressure force on the water, is replaced with battery. And the battery is rated in units of volts, and we'll talk a little bit about that a little bit further. So electric current, a flow of charged particles similar to the flow of water particles, only in this case it occurs in metal wires. And the conduction electrons, which are the electrons that are very loosely bound into the copper or aluminum or silver or whatever conductor we have, the electrons that are very loosely bound are the ones that carry the charges, and they're free to move throughout the whole length of the wire. So this is the concept that we have for flow of charges, and this will occur when there is an electric field. So we learned in electrostatics that when there's an electric field, if I have a positive charge at one location and a negative at another, then any charged particle in between will either accelerate towards the positive or negative, depending on what the sign of its charge is. The idea here is that it is in fact a flow of charged particles. Those particles are conduction electrons. They are the ones that are loosely bound in the wire itself, and so those are the ones that are going to carry the flow of what we call the flow of charge, which is in fact electric current. Water current, electric current, very closely the same thing. Electric current, flow of electrons. Water current, flow of H2O molecules. So those are and we try to draw that analogy so that you get a feeling for the sense and the meaning of voltage as electric potential. Positive protons, on the other hand, are bound with the nuclei of the atoms, and in solid materials, those nuclei do not move. Hence, the protons, which carry equal but opposite charge than the electrons, are also bound. They cannot move. The positive charges do not carry the electric current. Only the negative electrons are free to move, and therefore carry charge from one end of the wire to the other. In fluids, it's slightly different, although we're not really studying that in this section. Positive ions and electrons can constitute electric charge flow when we are doing in fluids. Sometimes we call this gaseous states or plasmas. Plasmas are a gas of positive and negative particles, such as we find in the upper atmosphere of the Earth, and these ions can be both positive and negative, and in a gas or in free space, then these ions can be both positive and negative. But for our concern here in circuits, we'll be looking at the negative electrons as the charge carriers. So which of these statements is true? Electric current is a flow of electric charge. Electric current is stored in batteries, both A and B, or neither A nor B. Electric current is a flow of charge. Electric current is stored in batteries. Well, the answer is that electric current is a flow of electric charge. That's exactly what we said before. It is voltage that is stored in batteries. But the potential difference, a potential energy difference, a ability to create a source of a positive terminal, positive conductor, which has deficiency of electrons, and a negative terminal, which has a overabundance of electrons. And that is what creates potential difference, or what we call voltage. And so the voltage will produce a current in a connecting circuit. The battery moves electrons already in the wire, but not necessarily those in the battery. Now that we've established that a battery, which has a positive terminal and negative terminal, which means we can think of it roughly as an abundance of electrons on one terminal, the absence of electrons and nuclei or atoms with their electrons stripped away on the other, gives us a difference in potential, which is able to drive current between the two. That current is what we call a rate of electric flow. And that is to say, it is measured as how many coulombs per charge are flowing through a cross-section of the wire per second of time. Similar to the way we define the coulomb, I'm not sure, just to clarify the definition of a coulomb, we can think of a coulomb as a fixed number of electrons, the charge on a fixed number of electrons. It tends to be about 10 to the 19 electrons. That is 10 followed by 19 zeros. Electrons constitutes a sufficient number to make 1 coulomb of charge. This is how we measure current flow. It is how many coulombs of charge per second are going through the wire. The speed of the electrons through a wire is, as we will see, extremely slow because of continuous bumping of electrons in a wire. So if we think of the electric field generated by applying the ends of the wire to a battery will in fact cause the electrons to move from the negative side of the wire to the positive side of the wire, or where the positive terminal of the battery is. But as they try to do so, the electrons end up colliding with the atomic nuclei that are in the wire, and this causes them to slow down, and they bump and slow down, and then they get accelerated by the electric field, and they bump and they slow down. So it's a continuously bumping, which gives a very slow speed of the electron. We can now say that charge flows through a circuit as measured by current, which we said was going to be in units of amperes. And this can only happen when there's voltage is established across the circuit in order to drive the electrons around in a loop. Now, up till now, we've only been talking about batteries like a 9-volt battery or a 3-volt battery or a 12-volt battery. These are batteries of fixed potential, and therefore, when I connect a wire across the terminals, and by the way, you should never connect a wire directly from the positive to negative because it will quickly heat up and either burn your hand or melt the wire. So generally we have objects that we put in that circuit called a resistor, actually keep the current at a lower amount. But we've been talking about conditions where if we have a constant voltage, then we have a constant flow of charge through the circuit, and therefore we have a constant number of amperes of current. Typically, and there was a big movie came out in this year, which if you're watching it this year was at the end of 2019, called The Electric Wars, which was a story of the interesting fight between Edison and Tesla regarding whether electricity should be delivered as what we call constant voltage or whether it should be delivered as alternating voltage. And Tesla finally won out, and he was correct, and there were reasons why alternating current works better, and some very good reasons, but it required us to establish the ability to make an alternating voltage. So by alternating voltage, we can think of, instead of, for example, a 12-volt battery, we can have a voltage source that goes up to 12 volts, goes down to negative 12 volts, it goes up to positive 12 volts, down to negative 12 volts, and oscillates up and down at a certain rate. And that rate is given by the frequency of the oscillation. Alternating current, electrons oscillate to and fro around fixed position. And the reason is very simple. If I apply a positive voltage, we send them in one direction, but immediately thereafter, before they've had a chance to move very far, we switch the voltage, and now they come back the other direction. And so they simply oscillate back and forth around fixed position. The movement is produced by a generator or an alternator that switches the sign of the charge periodically. So the generator is the voltage source, and that we will see in a following slide, that generates, if we have an oscillation or oscillatory voltage source, goes from, let's say, plus 12 to minus 12, or if we look at wall current or wall power, all of the plugs in the wall that we use in the home and in the office provide an alternating voltage of 120 volts, which means that there will be one conductor out of the two that are coming out of the wall, which vary in voltage from minus 120 volts to positive 120 and back to negative 120, and they do that 60 times per second. So the frequency of our electric current that is delivered from the electrical power plant is at 60 oscillations per second from max to min. So as a result, when that occurs in a circuit, that will make the current also alternate at that same frequency of 60 hertz, and the current will drive the electrons first in one direction, then a half a cycle later of the volt, when the voltage changes polarity, it will come back the other way, and it continues to do that every time at 60 times per second. And as we know, commercial circuits are used in most residential circuits throughout the world, and can be stepped up to high voltage for transmission over great distances, and they are able to do this with very small heat loss. And this is where AC power really does a great job. If we have a DC power, and that's over 10 miles from our home, and we are DC voltage, and we run a copper line from that station to our home, then if I'm producing 120 volts, I will have something much less when I get there. As a result, that's because the heating in the wire has generated losses, and I no longer can efficiently transmit electricity from a station far away to one close to our home. So AC circuits are used because small heat losses, and they can be stepped up to high voltages, and that means that we can run them up at high voltage and very low current, and then we can switch them back to much lower voltage and a higher current at the other end. The point of being efficient is to transmit the electricity or the electrical voltage without having a significant current, and we'll get more into that later. But commercial AC is what more is way thing. Commercial alternating current circuits is what we use throughout the world. Now, as I mentioned earlier, a conductor is any material having free charged particles that flow through it when electric force is acting on them. This is true for the ones we mentioned, which are copper, aluminum, silver, gold, cobalt, nickel. Many of the metals that we typically use have free charged electrons that flow through it when electric force is acting. Electric potential difference. It's a difference in potential between 2 points, one of which has an excess of positive charge, and the other point has an excess of negative charge. And as a result, this is what will make an electric potential difference. And of course, on our batteries, they're labeled positive and negative for the same reason. Now, charges in a conductor will always flow from higher potential to lower potential, and the flow of charge will persist until both ends of the conductor reach the same potential. If you don't want that to happen, which is generally the case, we want the flow of charge to occur continuously without interruption, then we need to have a pumping device known as the battery in the circuit. And the battery will make sure that there's no depletion of charge at the ends of the circuit or the end of the wire, so that there is always current flow, as long, of course, as the battery or the pumping device does not run out. Again, looking at our simple example, a voltage source, or what we call electric potential difference. We had the discussion earlier about the water flowing through, and in order to maintain a current of water, we have to have the pump in place. Otherwise, the two sides of the tank will just equalize in their level, and there will be no more water flow once that happens. And at that point, we say that the potential difference between the left side and the right side is zero. Just as the electric potential difference, if it ever drops to zero between 2 points, the current in the wire will also drop to zero. So voltage and current are very related, and we'll see by a very important law how that occurs. One way to regulate the amount of electricity flowing in a wire is to add a device called a resistor. In addition to having our generator, which is the electricity pump, which is what we call a voltage source, it'll be strictly determined by how many volts that the battery is rated at, then the work is done by pulling negative charges apart from positive ones, which are in the battery. And the electromagnetic induction at the generator terminals will provide the electrical pressure to move the electrons through the circuit. The battery requires that there is some work done to create this separation of charges, and that occurs within the battery. And if the battery is doing a lot of work, you will actually feel the battery get warm to your hand, to your touch. You can feel the heat generated in the battery as it does more work. And the switch in this case is allowing us to make the conductor continuous, just as the valve in the water pump allows the water to either flow or stop. Now, another thing we can do to regulate the amount or the flow or how many coulombs per second go through, just as we talk about how many gallons per minute will be flowing through the water circuit, is to add resistance to the line. And we can add resistance to a water line, or we can add resistance to an electrical line. And the higher this resistance, just as the more resistance we have in the line of a water pump, then the slower will be the current going through the loop. And therefore there'll be fewer gallons or liters per second per minute going through here. Electrical potential differences can be created by chemical batteries. They can be created by gasoline generators. They can be created by the electrical power plant that works by burning coal and other heat sources. And we'll talk more about how electricity is generated in the next two chapters, but in this one we'll just talk about the fact that these batteries are capable of producing a certain pressure. The pressure being the amount of force per unit charge to drive the electrons through the circuit and generate electricity. Chemical batteries, the work is done by what we call a chemical disintegration of zinc or lead in acid, and this chemical reaction is what is used to separate positive and negative ions within the battery itself. The negative ions going to the negative terminal, the positive ions going to the positive terminal. And in this way, energy that is stored in the chemical bonds is then converted to we call electric potential energy. Now, the batteries work in that they don't give us a fixed amount of charge, but they only generate a separation of charges as is needed by the circuit. So the more current that the circuit requires, then the harder the battery has to work to be able to generate that much current.